So here we have a situation where you are across the river over here, down here where the starting line is, and you want to swim to the finish line. So imagine this as a race. So when you race or when you engage in a competition, you want to get the fastest speed. In other words, you want to get from here to here as fast as you can. In other words, you want to minimize the time. Because when you race professionally, the officials will time you. So in this case, we want to minimize the time from start to finish. However, there's conditions. Well, in order to get from here to here, you have a swimming speed. Now, there's an option. You can swim from the start directly to the finish. That's one option. The second option is you can swim directly across and then run the rest. Or the third option is you can swim somewhere along here, maybe over here in this red arrow, and then run the rest, because there is a condition in terms of the speed. And in our case, you are running faster than you are swimming. So maybe sometimes you might think, well, maybe I shouldn't swim more than I run. Maybe I should run more than I swim. So in this situation, what we're going to analyze today is we are going to minimize the time. We want to reduce the time to travel from the beginning to the end, just like a normal competitive race. Now, here's the situation in terms of the dimensions. The width of the river is going to be 5. And from here to here, meaning the most that you can run is 10. And no, we are not going to run backwards. So some students might ask, well, Miss, can I not just run backwards and go forward from here, like go from here to here? We want to minimize time, not maximize time. So here we have a GeoGebra simulation where we could actually simulate what's happening in regards to the situation. So going to the conditions, your swimming speed over here is going to be 2 kilometers and your running speed is twice as much, 4 kilometers. And we have 3 conditions or 3 possibilities. You have a choice. Choice 1 is let's go swim directly from point B, which is a starting point, to point D. So if we did that, if we were to calculate the time, so I'm going to put here option 1. So option 1 is to swim only. And if you did that, how would you calculate the time for this? Now, what we know is that the swim speed is 2 kilometers per hour, and we know that the distance is that blue line that you see right over here. And how do we calculate the time when you have time, distance, and speed? So because we are minimizing time, we have to know the function. In other words, the popular one is velocity or speed. I don't want to use velocity. Speed is distance over time. But because we are minimizing time, we want to isolate for time. So time is, if you rearrange this equation, becomes distance over speed. And we have the speed. We just have to work for the distance if we were to swim only. So let's figure out the distance. Our distance in this case is from here to here. And this clearly is a right angle triangle. We know that the river is, I believe it's 5. And over here, it's a 10. So we know that the A value, B value using Pythagorean theorem, and calculate the C value. So over here, I'm just going to quickly just do this. In other words, we have the square root of 5 squared plus 10 squared divided by the speed of the swimming is going to be 2, which will give us around 5.6 hours. So that's option 1. Option 2 is to do the following. So option 2, which is to swim the least, because swimming is the slowest speed and you want to kind of spend more time running, the minimum distance for swimming would be the blue line directly across 5 and then run the full 10. So going back to the first one, option 1 is to minimize the distance. So you want to travel the shortest distance, but unfortunately you are swimming at the slowest speed. You're traveling at the slowest speed. So option 2 is let's try to reduce the swimming and maximize the fastest speed. But unfortunately, in this case, we're actually going to travel the maximum distance possible for option. But let's actually calculate the time. So what we're doing right now is actually calculating the extreme cases. In other words, we're calculating the endpoints of the function. So let's do option 2. So option 2 is swimming. So over here, I'm going to put time equals to total time is equals to time for swimming plus time for running, all right? And we know that time for swimming is distance of swimming over speed of swimming plus distance of running over speed of running, which we do have already. These two pieces we have. And in our option 2, we have these two pieces. So distance of swimming is going to be 5 kilometers over, in this case, swimming is 2, plus distance of running, since we're traveling the entire distance, if you look at the left, from here to here, that's going to be 10 in this situation. So that's 10 divided by 4, and if we calculate that, we end up getting 5 hours. So if you compare between option 1 and option 2, which one is better in regards to the race? Well, it would be option 2 because you traveled 5 hours. I mean, you finished the race in 5 hours versus 5.6 hours. So option 1, where we want to minimize the distance, over here using the arrow. So option 1, we minimize the distance, but we have to travel at the slowest speed. Now in option 2, we actually maximize the distance, but we actually reduce the amount of swimming. And if you notice, even though we traveled more distance, we actually save on time because we only have 5 hours versus 5.6 hours. So is there another case in option 3? And yes, there is. So option 3, actually, you can swim somewhere between point C and D, see the blue line there, and then we can just run the rest from A to D. So just to verify, so if you look at the time, I actually set the program in GeoGebra. So if you look at here, we swam right across the shortest distance of swimming. If you notice here, the time total over here, you can see over here, is around 5 hours, which we calculated. And if we go extreme, so point A to D, if you notice here, we have around 5.6 hours, which we calculated to be accurate. So let's actually move this around and see what happens. So we have 5 hours, and now it's going down to 4.8, 4.2, 4.7, 4.6, keep on going, 4.6. Oh, so we can see right away that it's going to be somewhere between 4.66, 4.6-ish, give or take. Somewhere around here would be the ideal time, because if I go after this point here, that 4.6 is going to become larger. So I know it's going to be somewhere around here, and we need to calculate that point. So let's deal with option 3. So option 3 says that you're going to be swimming somewhere between C and D, so along that blue line, and then run the rest. So in other words, I'm just going to draw this part here. I'll use blue. So this is your swimming, and over here I'll use orange. This would be your running. So going back to the function is going to be the following. Its distance is equals to, time, since we're minimizing time, when we reduce the time, distance over the speed. In our case, our total distance, I'll put T for total, is going to be the distance of the swimming. I'll put here swim, plus the distance of the running. And we know for a fact that we have the speed for swimming, which is 2 kilometers per hour, plus D over, I'll put DS for swimming, DR, and the speed for the running is 4. So now if you notice here, we have 2 unknown variables. Either you want to express T in terms of the distance of the swimming, or time in terms of distance of the running. And we need to make that choice right now. So in other words, what do you want? We don't have to call it DS. We can all use another external variable. I'll use X. So what do you want X to be? We have a choice. Either you want X to be the swimming distance over here, or do you want X to be the running distance? Or you have a third option. You can actually make from C to A also X. It really depends on what you want to do. So in my case, I'm going to let X be, let's try something different. Let C to A be the X. Because X is connected indirectly or directly to the blue line and the orangey line. So if I were to let X be from C to A, in other words, what would the distance of the running be? It would be from here to here. But we know the whole thing is worth how much? The most you can run is going to be 10. In other words, the distance of the running over here would be 10 minus X. So over here, I'm just going to modify this. So D of S over 2 plus, now this part here is going to be 10 minus X. So in other words, I'm actually expressing the time in terms of X. So here, T of X is equals 2. Now, over 4. Now we need to figure out d of s, or distance of the swimming. So the distance of the swimming is over here. Oh, I should be using blue, swimming, because usually blue colors relate to water. And what shape is the swimming distance related to? It's related to the right angled triangle. And we do know one of the sides for sure is from here to here, it's 5. So we can use Pythagorean theorem to actually figure out the blue area here with the x. So in other words, t of x is going to be equal to, I'm going to skip steps, I don't want to show all the Pythagorean work, it becomes 25 plus x squared divided by 2 plus 10 minus x over 4. So this is the function you're going to minimize or find the derivative afterwards. So now let's stress the restrictions for x. So now x is going to be from here to here, all right? Or so if you think about it, x, the minimum that x can be is 0. Imagine you not having this at all. What that means is when x is 0, what happens? When x is 0, that means you are running the full distance. Just remember that distance of running is equals to 10 minus x. And if x is 0, you run 10 kilometers. That's the most you can run. And x cannot be negative, because when x is negative, we don't want to run backwards and then forwards. Okay, that's number 1. And since we have the distance of running must be positive. Must be greater or equal to 0. So we're going to solve for this linear inequality. In this case, we're going to bring the 10 over, becomes negative 10, and then we just divide both sides by a negative. So when you solve for linear inequalities, you don't have to make that table chart, but the signs will change when you divide by negative on both sides, and we get this. So what this means is the most that x can be is 10. That's the maximum x can be. Because when x is 10, so you can imagine that when x is equals to 10, what's your running distance? 10 minus 10 is going to be 0. Can you run? You don't actually. So what that means is your distance of running is 0, meaning you're swimming all the time. So remember that option 1 when we swam the most. So in this case, our restrictions for x is going to be less than 10, but it has to be greater than 0. So when x is 0, that means we are running 10 kilometers. That's the most we can run. But when x is 10, we are running the least. We're not running at all, meaning we're swimming all the time. But some students might say, well, miss, I don't want x to be the pink line in the diagram. I want x to be the actual swimming distance. Okay, so let's actually let x be the swimming distance. I'm going to use blue in this case, so x is blue. Now, when you see that x is blue over here, I'll put here in blue, so your total time swimming is going to be x divided by 2, because x is your swimming distance, plus the distance of the running over 4. Now we need to figure out distance of running right now and express it in terms of x. So in this case, how is x related to your running distance? It is not directly, all right? It is actually, x is actually directly connected to the pink line, and this pink line is going to be directly connected to 8 and D. So in other words, we're going to be using Pythagorean theorem to solve for the pink line. So I'll use a pink for here. In this case, it's going to be the square root of x squared minus 5 squared. So I'm not going to show all the details of the Pythagorean theorem. Now, to get the running part, which is, I'll use the orange color, so this is your running part. So the running part is, the whole thing is going to be 10, but I don't want the pink part, so I'm going to subtract it from 10. So 10 minus the pink part. In other words, if I were to now establish the function, we have x over 2 plus something over 4. What's this something going to be? It's going to be the orange part. And that would be your function if you let x be the swimming distance. So your swimming, if you did it from this way, your function looks different. It looks a little bit different from mine, all right? But if you notice in both cases, the two parts are very similar in format. We have a rational function, like a square root function, and we have a linear function. Now, what happens if you want x to be the running distance? What's going to happen? Well, things are just going to be a little bit different. So let's let x be the running distance. So from here to here is going to be x. I'll use pink. That means from here to here is going to be 10 minus x. All right. And now we can link it back to the triangle or the blue line over here. I'll use blue here, over here. You can see the right angle triangle, and let's link it. So what would the swimming distance be? Well, you're going to be using Pythagorean theorem. So in this case, we want to find the hypotenuse, the longest side. It'd be 5 squared plus 10 minus x squared. So I'll use pink to get the third type of equation. If you want x to be the running distance, it would be something over something Okay, so this 2 becomes the swimming distance, which is the blue part here, square root of 5 squared plus 10 minus x squared. So we have a radical function, square root function, and the other one, the swimming distance, the running distance, is just x over 4. So again, look at the format on all 3 options, depending on what you want x to be. Notice how we have a linear, something over, okay, and then we have a radical, radical, radical. I'm not going to go through the restrictions for this. It's sort of the same idea. So just to continue with the original way that explained this function, where x is from a to c, so we don't need this piece anymore. So we can change this because that's not my x. My x was from a to c. From a to c, okay. So the rest of the steps I'm not going to show you because it's calculus. I mean, it's all calculus techniques. So make sure you take your derivative of this function, which we have before. I mean, of a radical function. You solve for the zeros and when it's undefined. All right, that's the first step. The second step is do your first derivative test to show that it's a maximum or a minimum. In this case, you should get a minimum. And then over here, number 3, and check your extreme values, your extreme points, or I'll call it the end behaviors. In this case, we don't have to use limit notation. We just sub in t of 0 into the function, t of 10 into the function, and we're going to get one of the extreme cases. So one was, I believe, 5 and 5.6. All right. So this one means you are, when x is 10, you are not running at all. You're actually swimming. We got 5.6. This is just swim only. Now 10 means from here to here, right? And if this piece was 0 over here, that means we run the entire piece. That means we are running and swimming, and we got 5.0. So the third thing you're going to get is you're going to get a critical point here, which you proved as a local minimum, and you should get this number up here, 4.66.